When a missile is fired at a city, the people inside it have minutes, sometimes seconds, before it arrives. The only thing standing between that missile and its target is a system that has to detect it, calculate where it's going, decide whether to engage, launch an interceptor, and guide that interceptor to a collision point, all faster than most people can process what's happening. Air defense systems are some of the most technically demanding machines ever built, and understanding how they actually work reveals something important. They are not impenetrable shields, they are carefully engineered layers of probability, each one designed to reduce the chance that something gets through. The difference between a good air defense system and a great one isn't just technology, it's how intelligently those layers are combined and how quickly the whole architecture can respond to a threat it wasn't specifically designed for. The foundation of any air defense system is radar. Before anything can be intercepted, it has to be found. Modern air defense radars don't work like the rotating dish antennas most people picture. Systems like the Patriot use phased array radar, a flat panel covered in hundreds or thousands of small antenna elements that can electronically steer the radar beam in any direction almost instantly without any physical movement. This allows the system to track dozens of targets simultaneously, updating their positions many times per second. The radar picks up the velocity and flight profile of an incoming object, and the system's computer begins classifying it immediately. Is this an aircraft, a drone, a cruise missile, or a ballistic missile? Each one has a different speed, altitude, and trajectory signature, and the classification determines everything that happens next. A wrong classification at this stage means either a wasted interceptor or a missed threat, so the software doing this work is among the most carefully validated code in any defense system. Once a threat is identified, the fire control computer begins solving what is essentially a geometry problem at extraordinary speed. The incoming missile is moving. The interceptor hasn't been launched yet. The computer has to calculate not where the threat is now, but where it will be in the future, and specifically, the point in space where an interceptor traveling at its own speed can arrive at exactly the same moment. This predicted collision point is called the intercept solution, and computing it accurately requires knowing the threat's current position, velocity, altitude, and trajectory, then running continuous calculations as all of those values change. The entire process from detection to launch decision can happen in seconds. In some systems, it's largely automated. In others, a human operator confirms the engagement. Either way, time is the resource that's always running out. Different systems are built for different layers of this problem, and that layered architecture is deliberate. Israel's Iron Dome, developed by Rafael Advanced Defense Systems with significant U.S. financial support, is designed specifically to intercept unguided rockets and short-range artillery shells fired from ranges of 4 to 70 kilometers. Each battery covers roughly 150 square kilometers. One of its most important features is selective engagement. If the system calculates that an incoming rocket will land in an unpopulated area or open field, it doesn't fire. It conserves its interceptors for threats that are actually going to hit something. Each Tamir interceptor missile costs around $50,000, which sounds expensive until you consider that the rockets it's shooting down often cost a few $100s each. The financial asymmetry is a real strategic problem, and selective engagement is one way the system tries to manage it. Since its operational debut in 2011, Iron Dome has intercepted thousands of rockets over Israeli territory, and its performance in high-intensity conflicts has made it one of the most studied air defense systems in the world. The Patriot system operates in a different layer entirely. Built by Raytheon and operated by more than 17 nations, it's designed to engage tactical ballistic missiles, cruise missiles, and high-speed aircraft at far greater altitudes and ranges than Iron Dome. In its most advanced configuration, the PAC-3MSE interceptor doesn't destroy its target using a proximity warhead that explodes nearby. It uses direct hit-to-kill technology, physically colliding with the incoming missile and destroying it through the sheer force of impact. Hitting a ballistic missile warhead traveling at several times the speed of sound with another missile is an engineering achievement that took decades to develop. The Patriot's phased array radar can track up to 100 targets simultaneously, and the system has been used in combat more than 250 times across multiple conflicts by 5 different nations against everything from ballistic missiles to cruise missiles to unmanned aircraft. Higher up in the defensive architecture sits THAAD, Terminal High Altitude Area Defense. Where Patriot operates primarily within the atmosphere, it's designed to intercept ballistic missiles at the very top of the atmosphere and just beyond it during the final phase of their descent. It also uses hit-to-kill technology, and its engagement altitude means that even when it works perfectly, the debris from a destroyed warhead falls in a much more dispersed pattern, reducing the damage that even a successful interception might cause on the ground. THAAD's AN/T PFI-2 radar is one of the most powerful mobile ground-based radars in the world, capable of detecting a baseball-sized object at ranges of several hundred kilometers. The system is specifically optimized for the threat profile of short to intermediate range ballistic missiles during their terminal phase, and a single battery provides coverage over a significantly larger area than a Patriot battery, making it a critical component of any layered national defense. At sea, the Aegis ballistic missile defense system extends this coverage further. Warships equipped with the Aegis system and SM-3 interceptors can engage ballistic missiles during the mid-course phase of flight while they're still coasting through space before they begin re-entry. This is the longest phase of a ballistic missile's flight, which means more time and more distance in which to engage. An Aegis-equipped destroyer positioned in the right location can defend a large area from threats that a land-based terminal defense system might not reach in time. The US, Japan, South Korea, and several European nations all operate Aegis-equipped ships as part of their layered defense architecture. The flexibility of a seaborne platform able to reposition anywhere in the world's oceans within days gives Aegis a strategic mobility that no land-based system can match. These systems work together, but none of them work perfectly. Saturation is the most straightforward way to overwhelm any defense. Fire enough missiles simultaneously, and some will get through simply because the defender runs out of interceptors or engagement windows. The October 2023 Hamas attack on Israel demonstrated this clearly, with thousands of rockets fired in coordinated salvos that strained even Iron Dome's high-volume interception capability. Each interceptor has a cost measured in tens of thousands to millions of dollars. Each incoming rocket might cost a few hundred. An attacker willing to fire enough of them can exhaust a defense economically before exhausting it physically. This cost asymmetry is one of the central unsolved problems in modern air defense, and it drives significant research into lower-cost interception methods, including directed energy weapons and laser systems, which have essentially zero marginal cost per shot once the infrastructure is in place. Israel, the United States, and several other nations have active programs developing high-energy laser interceptors specifically to address this imbalance. Decoys and electronic warfare add another layer of difficulty. A sophisticated attacker can deploy objects alongside a real warhead that are indistinguishable to radar. The defense system sees multiple targets and has to choose quickly which ones to engage. And if it fires interceptors at decoys, the real warhead arrives uncontested. Electronic jamming can degrade radar performance, feeding the fire control computer corrupted data and pulling its intercept solution away from the actual threat. These aren't theoretical vulnerabilities. They're actively exploited in real conflicts, and they're why no military that operates air defense systems describes them as guaranteed protection. The newest challenge is hypersonic glide vehicles, weapons that travel at speeds exceeding 5 times the speed of sound while maneuvering unpredictably, unlike a ballistic missile which follows a predictable arc. Traditional air defense systems are built around trajectory prediction. If the target maneuvers after the intercept solution has been calculated, that solution is suddenly wrong, and there may not be enough time to recalculate and reposition the interceptor. Russia, China, and the United States are all developing or fielding hypersonic weapons, and the defense community is candid about the fact that current air defense architectures were not designed with these threats in mind. Upgrades to radar sensitivity and interceptor maneuverability are underway, but the gap between the speed of the threat and the capability of the defense remains a genuine and openly acknowledged problem. What all of this adds up to is a picture that's more honest than the one usually presented. Air defense systems are remarkable technology. The countries that operate the most capable air defense architectures in the world layer multiple systems on top of each other precisely because no single system is enough. The goal is never to make attack impossible. It's to make it difficult, costly, and uncertain enough that the calculus shifts. That's what deterrence actually looks like in practice. Not a perfect shield, but a set of compounding obstacles carefully designed to raise the price of getting through.